Okay, I guess I may as well start. Professor Nilsson is unable to be here today, so he asked me if I would introduce myself, which I will do, or try to do. My name is David Rumelhart. I'm in the psychology department here. My field is cognitive science, and which, in case you don't know, is somewhere in the interface between cognitive psychology and artificial intelligence. Over the last 12 years or so, I've been working in an area which has a variety of names. In the perhaps the most familiar in the field of artificial intelligence is what's called Connectionist AI. The idea, I actually prefer several other names, such as the study of what I call brain-style computation. The basic idea is to imagine that the kind of computer that we have to work with isn't organized, isn't as our conventional computers are organized, but the kind of computer that we have to work with is a computer that works more or less the way the brain does, and processes information more or less the way the brain does. Now, if we look at how the brain actually processes information, of course we don't know in great detail. But we know that there are many design characteristics, or many characteristics of the brain, that yield different kinds of optima. That is to say, the kind of design we expect to see in the brain is rather different than the kind we expect to see in a system which is, say, made out of silicon. Just to give a simple example, if we think of the timing involved, turns out that, relatively speaking, neurons are incredibly slow information processing devices. They process information on the scale of milliseconds, or even tens of milliseconds. Whereas if we look at our components in our conventional computers, we see that they process information on the order of nanoseconds. So we're talking about a factor of 1,000,000 difference in processing speed between our computer, the kind of computers that we're used to working with, and the kind of computer that the brain is. Now, this has presumably, nevertheless, the brain is a pretty effective information processing system. We've had a very hard time mimicking it, even though we've had systems which were very much faster than the brain. One question is why? And the answer, roughly speaking, is that the brain seems to process information much more in parallel. There doesn't really seem to be a CPU that corresponds to the kind of CPU we have in our conventional computers. Rather, it seems that each of the billions of neurons that we have operates pretty much as an independent processing element. And the way information is processed is essentially we have billions of very simple processing elements that communicate with one another in very simple ways. In particular, they communicate with one another by sending very simple messages from one processing element to another. Those messages are pulse trains in the brain. Typically in our models, we characterize those messages as real-valued numbers of some kind. So we think of two neurons, two processing elements communicating with one another by one sending what corresponds roughly in the brain to we think of as like a mean firing rate. Sends a mean firing rate to another neuron. And the question arises, suppose that our whole information processing system consisted only of these little neuron-like elements and connections among them. What kind of algorithms would be good to do the sorts of things that are done in AI? How could we make a system be smart that was created out of just these very simple processing elements, interconnected in these very simple ways? Now, we know that we could These processing elements are surely no simpler than a transistor. Surely we could think of them as logic gates if we wanted to. However, if we do think of them as logic gates, we have to think how many logic gates, how many steps do we have to go through in order to compute a particular kind of do a particular kind of computation. And the answer is generally that it takes a lot. And so what we have to do is put more and more of the information processing in parallel and less of it sort of serially. We don't get very many serial steps in the few hundred milliseconds that it takes a human being, for example, to recognize a scene, or to tell whether a sentence is true or false, or to do many of the things that we try to do in our AI programs. So now, what I want to talk about today is one subset of this body of work on connectionist AI, and that's the subset that has to do with learning. Now, imagine that our computer consists of simply a set of these little elements, think of them as little neurons, which are connected to other elements in a vast network of interconnections. And we wish to, in some way, compute something with this. We wish to determine, in some fashion, some computation. So the way we think about it is this. We imagine that we have many little processing elements connected to one another in some fashion, arbitrarily more or less. Each connection we think of as being weighted. There's some strength of connection, and if this is unit I and this is unit J, we think of Wij as representing the weight or the strength of connection. And what that means is that the degree to which unit I changes the behavior of unit J is measured by the magnitude of this Wij. Its sign may be positive or negative. If its sign is positive, that means activity in unit I increases activity in unit J. If the sign is negative, then activity in unit I decreases activity in unit J. Typical equation that we use for this is that we say that we get what we call the net input into a unit, which we'll call net input into unit J, is going to be the sum of Wij of A sub I, summed over I, where A sub I represents the activity associated with unit I. So we get what we call a net input, which is just the sum, the weighted sum of all of the activity. And then the output, Aj, is simply equal to something like this. 1 over 1 plus e to the minus net j, where net j is given here. And that's a curve which looks something like this. If the net is a negative number, the unit will turn off. It will have 0 value. If the net is a big positive number, the unit will turn on. So if the net is just exactly at 0, then the unit, if it's 0, since e to the 0 is 1, we get a half, so that then it will just give out a value of a half if the net input is exactly balanced. And in this way, we get something that approximates a logic gate, for example, if the values are very high, but in the middle, it's sort of a graded value. So this is a typical way in which we model the behavior of these networks. We write down equations such as this that describe the behavior of individual units, and then we write down this depends upon these parameters W. Now it turns out it's possible to show that networks of this kind are universal computational devices. That is to say, we can compute, or put another way, we can approximate absolutely any function as closely as we like by a sufficiently large network of this kind. So the way in which we're going to carry out, imagine that computations are carried out, is that we'll have some of these units which we designate, say, as inputs, and some which we designate as output. And then we have some in the middle, which for no better term we call hidden units. And we can show that this kind of organization is sufficient to compute essentially any function, any possible function, from inputs to outputs, provided we have enough, say, hidden units here. And what we need to do, though, in order to make it compute a particular function, is to find the right values of W. So learning in a network like this involves simply finding the pattern of connectivity that will cause the network to carry out the desired computation. So what we've done in Connectionist AI is reduced the problem of learning to a very simple problem. It's a problem which we might call parameter estimation, namely finding a set of parameters that will compute the desired function. Now, it turns out that if we look at all the learning algorithms in Connectionist AI, we can view them essentially as approximations or statistical methods for trying to estimate a large number of parameters from a set of data. This is all learning from example, typically the way it works. So to review then, the basic idea is this, and I'll draw sort of a canonical network now. The basic idea is that we have some inputs, x. Now, the way we represent our inputs is always as a vector. So we need to be able to say, we think of the data, the input data, as represented by a set of numbers. And the number of numbers we get, depends on the number of input units we have. But what we do is we take a vector and we map it by setting the activation value of each of our input units equal to components in the vector. So this is a mapping from input vectors to output vectors. Then canonically we imagine that there's some number of layers, so that each unit in one layer, for example this we call the input layer, each unit in the input layer maps onto a unit in, let's say, a hidden layer, which then in turn maps onto units in another hidden layer, and so on, until eventually they map onto units in an output layer. Now what I've drawn here is an example of what's called a feed-forward network. Feed-forward, oops. So we think of this as a feed-forward network in that it takes an input x and carries out a sequence of transformations. If we think of this as a vector, if we think of x as a vector, it appears in some space, some vector space, and as we move from layer to layer, we're transforming that space from one vector space to another. The transformation is a nonlinear transformation because of the nonlinearities in the units. The fact that they're these sigmoid-shaped units means that what we're doing is a nonlinear transformation from one layer to the next, to the next, to the next, until we map from vector x to vector y. So the input is a vector and the output is a vector, and learning is discovering a set of transformations, T1, T2, and so on, a set of transformations that will map X to Y. And each transformation is characterized by a pattern of connectivity, a set of weights, W. So this then is the problem of learning in connectionist format. Now what we have typically is a set of pairs of data, that is input-output pairs, and these are observations that we might make in the world. And the game is to try to take these set of pairs and discover a set of transformations that will predict the appropriate output values given an appropriate input value. Now, to a first approximation, we could imagine this simply storing the pairs. So we take a set of pairs of input and output pairs, we put them in the network by finding a set of weights which are consistent, which do the right mapping, and we do this for a large set of pairs. Then given any pair, any x value, we can figure out what the correct y value is just by plugging the x value into the network, and it gives us out the y value. But what we're really interested in is not simply memorizing a set of pairs, but what we're really interested in the learning domain is having a set of pairs such that given a brand new example of an x that we've never seen before, we get the right value out for y. This is what we call the generalization problem. So just simply, we could store these pairs if we wanted to in a table, and do table lookup. But that wouldn't be very interesting. What we really are interested in is generalization. And these networks have an interesting property with respect to generalization. In particular, if we just look at the behavior from one level to the next, we know there are constraints on how similar the representations are at the two levels. So to a first approximation, if we take level layer I and the map from layer I to layer j, that is I to I plus 1 rather, similar patterns, things that are similar to each other, that is vectors which are near each other in vector space, at layer I have to also be somewhat near each other at layer I plus 1. So there's this constraint that similar vectors are mapped onto similar vectors. But it turns out that if we go through enough levels, eventually we can pull them apart. And we can impose essentially a new similarity structure. And the idea is to discover a similarity structure so that things that are near each other in this new similarity structure are things that we wish to respond similarly to. And this is what the whole learning problem is about in connectionist AI. Now, I'm not going to go through too many details here, but I'm going to go through a few. First question is, well, how do we figure out what value these connections should have in order to properly mimic the desired function? How are we going to figure out what value? Now, the answer is we have what we call a learning algorithm. And a particular learning algorithm that I want to talk about is one that's called backpropagation learning. This is an algorithm that works in the following way. The idea is that you set some goal. In particular, let's say you set some what we call an error function. And let's say that we say that the error function, the goodness of performance of the network, say is given by the difference between the target and the actual output value squared. We present a pattern to the network, and we're going to score it by saying, well, how close is the pattern, is the output to the desired output, what we actually observed, or what it should have been. And we're going to use that mismatch as a measure of how well we're doing. Now, what we're going to do is arrange it so that in the learning, we can now view learning as an optimization problem. Once we have a measure of how well we're doing, we can say that we can say, well, what we want to do is make E as small as possible. We want to have as little error as possible. And we want to find those values of W, those weights, that make this error as small as we can. And we know many methods. There are many numerical methods for doing this. But we want to find a numerical method that's well suited to brain-style computation, so-called. And one such method is a method that is called steepest descent, or a gradient descent method. And what we do is simply this. We take the derivative of the error with respect to some weight in the system, Wij. So what we can do is if we fix all the weights but one, say Wij, we plot E, it's going to look something like this. If we make Wij too big out here, then the error will go up. If we make it too small, then the error will go up. But there'll be one point right here where the error is at its minimum, given the value of all the other weights. Now this is true for essentially, so what that means is that if the derivative is positive, then we want to reduce the weight. It means it's too big. If the derivative is negative, we want to increase the weight if we want to find this minimum point. So what we're going to do is say that the change of weight, Wij, is proportional to minus the derivative of E with respect to Wij. This is what's called the steepest descent in numerical analysis. This would be a steepest descent algorithm for finding the minimum value, or those values of W which minimize this error function. And essentially, what you can do, I'm not going to go through this, but if everything in the system is differentiable, that is, the activation functions, these are nice smooth functions, so that things are differentiable, we can actually apply the chain rule, and we can compute the derivative directly. We can just simply compute the derivative of this error function with respect to any parameter in the system. And backpropagation learning is sort of a method for doing that. It's a simple method that involves, it's called backpropagation because we're actually unfolding the chain rule as we pass information backwards through the system. We're simply computing the derivative explicitly. And we do so by essentially unfolding the chain rule. This is what's going on. In AI, this turns out to be equivalent to what we call the credit assignment problem in AI. And what we say is that, or blame, if you will, what we say is that the blame associated with any given weight is proportional to the derivative of the error with respect to its weight. So we will blame a weight if, in fact, a small difference in the weight makes a big difference in the error. We'll assign more blame there, and we'll move that weight a little more. If changes in a weight have no effect on the error, which it might, for some weights in the system it'll just be flat, well, in that case we don't care. We give no blame to that weight. It wasn't responsible for the behavior that we observed. It wasn't responsible for the error that we observed. Okay, so this is probably now let's just back up a moment and talk about what it is we've done here. What we've done, first of all, with respect to what's normally done in AI, is that we've developed a very simple representation of knowledge. All knowledge must be represented by a vector. That's it. Secondly, we have a very simple representation of a computational system. A computational system is simply one which maps information through layer by layer by simply taking weighted sums of activities in different layers, and it's all completely homogeneous. There is no executive, there is no routines or subroutines or anything like that. It's all a homogeneous mapping process. And once we've done that, we simplify the learning problem to be a problem of parameter estimation, no more, no less. And that makes learning, first of all, this is an extremely general learning device. Applies to anything. And turns out it would be what Alan Newell would call a weak method. It's a weak method because it's extremely general and uses very little domain-specific knowledge. I'll describe how you can get some domain-specific knowledge in it if you like, but it uses very little. It simply takes examples and attempts to induce the structure of the problem from those examples. So what I'm going to do for the rest of the hour is to talk about some examples to make it a little clearer how this system might work. I guess the first example that I'm going to talk about is sort of one of the more famous ones, but just to illustrate. So, well, I guess this won't be one of the more famous ones since I don't have that picture with me. I'll just illustrate with another one. This is a simple-minded idea that works in the following way. Imagine that what you wanted to do was to learn to hear the difference in, say, a sonar signal between a case in which you had just a rocky bottom of a bay, let's say, and a case in which you had a rocky bottom of a bay, but on the bottom there was a shiny metallic object, which was a mine of some sort, let's say. So you're just trying to pick up the existence of a particular shaped object. Now, the way in which you can do that with active sonar is you send out a pulse and you listen to the echo. And there'll be skilled sonar listeners are able to listen to this and pick out, tell you which of two cases they're listening to. And what we would like to do is ask, well, can we train a network to be able to make the same discrimination that people make in this kind of a case? And here is a simple example of such a network. What we have here is a set of, in this case, 60 input units. And what we do is we take the spectrum in the relevant regions, just the power spectrum of the signal over the relevant temporal domain. We know roughly when the echo is coming back, so we know where to take our spectrum. And we scale it so it goes between 0 and 1 in this instance. And we simply give an activity value on our units which correspond to the power at different frequency bands in the input. We then use that as our inputs. In this case, we have a single layer of hidden units, and we map the two output units. The two output units, in this case, correspond, one of them to yes, the signal was present, and the other, no, the signal was not present. So this is just a simple way of trying to do this mapping. What we can do in a case like this is to try to compare this method to other sorts of methods that have been developed for doing this kind of a task. And here is one such example. the method of estimating the parameters here was the method that we described, the backpropagation method. And what we have here are first the performance of humans. Typically what we'll do is we take the data that we have and we divide it into two parts. One part we call a training set, one part we call a test set. And what we do is we train the network on half of it, and then we test it on the other half to see how well it generalizes to the new cases, because those are the ones we're interested in. Now, if we take people, what we see is if we train people to do this task, they can get up to be about 90% correct. It's not an easy task, but they can do a pretty good job. And this is if they practice on a given set. If they go to a new set, they get about, say, 85% correct on the test set. There was in this particular instance, there was a sort of expert system that had been developed to try to carry out this same task. And that was what's called here a feature-based classifier. And the particular expert system was pretty good, performed a little bit better than people on the training set, got about 92% correct. But more importantly, on the test set, by the way, the training set, I should say, was a set that was used to, there were some parameters in the expert system, and they used this to estimate what those parameters should be. On the new data, the test data, they again performed about the same as people. They got about 84% correct. In the Connectionist network, what we observed was that with 12 hidden units, it had no trouble whatsoever essentially memorizing the data in the training set. It got those just about all right, 99% correct. In the test set, however, what we see is that it generalized at a level, in this case, of about 92% correct, which was a bit better than people or the expert system. And this is typically what we find in many of these areas. By allowing the network to try to learn these maps, we find that its performance is generally at least as good as essentially various kinds of engineered systems, such as this feature-based classifier, and usually comparable, although generally not quite as good as people who are highly skilled at the task. In this case, the human subjects weren't quite as good as the network, but often we find that human subjects at these tasks are still a bit better than the networks or any other methods that we know about, actually. Now, this is a signal processing task, more or less. And the learning here is perhaps not as interesting to people in AI as other kinds of learning. But this sort of illustrates the general feature of these connectionist systems. We typically have a set of examples. We train the network on those examples and see how well it does on the training. But more interesting, we then give it a set of examples it's never seen before and look to see how well it performs on those. And this is sort of a pattern recognition problem. Not all application areas of these networks are pattern recognition per se. And I want to talk next about another application area in which was more common or familiar, I think, to people in AI. And that's a method of trying to store or deal with what we might call conceptual or more structured kinds of information rather than just sensory signals. Although I should say that on whole, AI has been less good at dealing with perceptual sensory motor processing than they have been at dealing with logic-based kinds of processing, which is where we've been the best. With symbolic kinds of processing, I should say. I don't know how legible this is, but this is what we would call a semantic network. It's a kind of information that should be familiar to many of you. Basically, it's a tree structure. We have at the top living thing. We have living thing broken down into two classes, plants and animals. We have the plants broken down into two classes, trees and flowers. Flowers broken down into rose and daisy, and trees into oak and pine. And birds and fish. Animals are broken into birds and fish, and birds are canaries and robins, and so forth. Essentially, we have a network here. And typical rule is the so-called rule of inheritance, in which if we can conclude that a pine can grow because a pine is a tree, and a tree is a plant, and a plant is a living thing, and living things can grow. So we have what's called inheritance properties. And this can be viewed as a summary of a lot of facts. Just simply a way of summarizing a lot of facts, that this particular data structure is often used in AI type programs to store this kind of symbolic information, and largely because of this nice property of inheritance. And there are some nice features that are illustrated by these dotted lines, or two additional features illustrated here by these dotted lines. If we see a new bird, say a sparrow, all we have to do is say a sparrow is a bird, and we get for free, for example, that a sparrow can fly, that a sparrow can move, a sparrow is living, and so forth. All that comes for free once all we have to do is say that a sparrow is a bird. And then it has then we can make all these conclusions. So once we build up this structure, we get sort of a lot of information that is just comes for free in the structure. That's a kind of generalization that's occurring. It's a generalization over, let's say, birds. Anything we say is a bird, we ought to also conclude all these other things, more or less, except when we come up against cases like ostrich. We say an ostrich is a bird. We get for free that an ostrich can fly, but we may not want it, since ostriches can't fly. Therefore, we might have to add this sort of special information down here that an ostrich can't fly. Now, so this should be familiar to most of you. How would we store in a connectionist network, how would we store that kind of information? It wouldn't look at all like this, but there is a way, and what I want to talk about now is a way of doing that and some of the properties of this kind of a representation. We're now talking really about how to represent information of this kind. Now, if we look here, we see we have what's a typical connectionist network, and it's organized in the following way. There are a set of units here, which I call nodes. And there's one of these units for each essentially node in the tree. There'll be one for pine, one for daisy, one for flower, one for living thing, and so forth. Every node in the tree will have a relevant unit here in this representation. Over here, there are various arcs that can appear in the tree. For example, is a, or has, or can, and so on. And in this particular instance, there are 4 different kinds of arcs. So I'm going to have a unit corresponding to each arc type. Now, the way I'm going to arrange it to store some information is I may say that a canary, I'll turn on a unit here that stands for canary, and I'll turn on a unit here that stands for ISA. And what I want to have happen here is turn on units that correspond to all the things that a canary ISA. So in this case, if I turn on canary and ISA, it should turn on up here, for example, it should turn on bird, living thing, animal, and so forth. And then if it does that, I'll say, okay, it's stored that information. Similarly, if I turn on canary and can, it should turn on over here. It should say a canary can fly, it can sing, it can move, and can grow, and so on over here. If it does that, I'll say, okay, it's stored that information. So I can take all the information that exists in this network and store it, that exists in the tree, and store it in my connectionist network by using the learning rules that I talked about. Now, what I'm going to be interested in looking at, though, is after I've stored a bunch of this information, what happens if I give it something new? Does it generalize correctly? What happens if I tell it that a sparrow is a bird? Will it know without any further information that a sparrow can fly? This is one of the things that I would like to deal with. Secondly, if you'll notice the particular structure that I've built here, I've built it for a particular reason. I have these nodes which correspond to things like sparrows and canaries and salmon and sunfish and what have you. That they this is what we call a localist representation. What we do when we turn on canary is we turn on one unit only, and we turn on the canary unit. But what we would like to do is get some, what we call distributed representation here. Some pattern that corresponds to canary. And what we would expect is that, because it's doing a transformation from one space to another, what we'd expect is that if two animals or plants were similar to each other, they should have similar representations. It should learn how to represent these things, and similar things should be represented similarly. This is sort of the feature of connectionist systems. They're kind of similarity based. So I'm going to be interested in looking at the pattern here to see how that works. Well, I don't have too much time, so let me quickly talk about the results from this particular experiment. First off, here is an example of the representations that were learned in this experiment. What I have here is, for example, here it says pine, and we see that pine, when I turn on pine, it turns on, at the level of those representation units that I mentioned, a pattern. In this case, the pattern is plus, minus, plus. That is, it turns on the first one, turns off the second one, turns on the third, turns off the fourth, fifth, and sixth, turns on the seventh and eighth. So it creates a pattern, and we can compare the patterns, for example, for oaks and pines and so on. And one thing we notice here is that whenever it's a plant, the first unit in this representation element is on. It's a plus. Whenever it's an animal, the first unit is not on. It's either a minus or, in this case, a dot. For example, a dot simply means that it's in between, since they could be all the way on or all the way off or in between. And a dot means in between. Basically, what we see is that the first unit has learned to signal whether it's plant or animal. We also see that the fourth unit here, interestingly, if we look at the plants, we see that the fourth unit is minus, off, in the case of trees, and plus, on, in the case of flowers. When we look at the fourth unit for birds and fish, we see that the fourth unit is on for birds and not on for fish. So basically what's happened is that it's created a representation of this data in order to make things somehow more concise. And we can then ask, well, what happens if I tell it something new? What happens if I tell it that, say, in this particular case, I tell it that a sparrow is a bird. So the way I do that is I simply say a sparrow is a bird. A sparrow is something it's never seen before. So I tell it that a sparrow is a bird and allow it to change the connections from the new sparrow unit to the representation units. And what I get is a pattern here which, as I'll show you in a moment, is very much like somewhere between robin and canary, more like robin than like canary. But I tell it that it is a bird, and then I look to see what it says about other things. In this case, it says that it can fly, can move, can grow. It says that it has wings, feathers, and skin. It says that it's living. It says that it's red. That's because I told it robins were red, and it's sort of assimilated sparrow to robin. You can see that it gives a strength 0.7. All the others have strength 1. That means that it's certain of it. It gives a strength 0.7, which means it has a 0.7 probability that it's a robin. But it knows that it's a bird, an animal, a living thing. For whatever reason, it gives it a 0.1 probability that it has gills or scales, which it doesn't. In any case, we see this kind of generalization that occurs automatically in this case. It has essentially inferred very much of the same structure that we get from our usual inheritance schemes. Except here, it simply inferred it from the data. In this case, I also trained it on ostrich. I trained it that an ostrich was a bird, but that an ostrich couldn't fly. It had no trouble assimilating this information when I told it about ostrich. So I then told it about another bird. And about this bird, I told it, well, this bird is, this thing is a bird and it can't fly. And what it did in this case was essentially created, I had in mind, say, an emu. An emu is a bird, an emu can't fly. And what it did was to create a representation that was very much like the ostrich representation, because that was the only bird it knew about that couldn't fly. And on having done that, then what we would find is that it would answer things like it was big, and so on, all the things that were true of ostriches, because it simply had assimilated emu to ostrich. Well, those are just two examples of how we can start with these very simple connectionist ideas and a very simple idea of learning, and we can get the network to store information in a way which is first of all sensible from the point of view of performance in things like learning how to discriminate, make difficult discriminations, and also so that it will generalize correctly to new cases, as in the case, for example, in the sonar example, or in this example, where just telling it now, after I've shown it a bunch of examples, telling it something is a bird, it infers correctly all the more or less appropriately that it can fly, that it has feathers, and so on, all the properties that you would hope that in AI, in standard technology, we get from this inheritance property. By now, these connectionist learning models have been applied to many, many domains. Many times, I think, with very good success. And I think what I'll do now is simply stop and open the floor to any questions that anybody might have. Yes?
I have a couple of questions. First is, how would you define learning? What needs to learn compared between humans, feature-based, and connectionist learning? gave some units who were sharing, representing unrelated features like the tree versus flower and bird versus fish. Is this desirable in principle in your view?
Yeah. The first question has to do with about time of learning. The answer is that it takes quite a few examples in general for these networks to learn. Partly, let's say, as opposed to how many examples a human being might have to see of one of these cases. Although, as we saw in the sonar case, the human saw exactly the same data that the network saw. And probably it took the human longer, but that's simply because the human simply took it longer, takes people longer to listen and so on than it takes our fast little computers to simulate it. But in terms of number of times seeing the examples, and the networks probably saw the examples more. So one of the disadvantages of this system is, in fact, that it takes a long time. It takes a lot of data. One of the reasons that it takes so much data is that there are very few assumptions built in. So there's a trade-off between generality and degree of, and the amount of data that it actually takes to constrain the network sufficiently. So what we find is that humans naturally make assumptions about the domain in which they're working. And these assumptions are constrain the data space, constrain the possible set of things that they'll consider. Whereas the networks, by and large, have no prior biases. So you need enough data to sort of constrain them enough so that they don't come up with some trivial, tricky way of trying to solve the problem, which is what typically would happen. They would find some little peculiarity, if you just used a few examples, peculiarity of the examples, and focus in on that. So this is one issue. Now the feature-based or the expert system type, it's not clear how long that takes to learn if you include the amount of time it actually takes to design the expert system. Probably the networks are faster if you include design time. But since this feature-based system, for example, had fewer parameters in it than the connectionist network, it probably took less data to constrain those parameters. But a lot more work on the basis of people to try to decide what the parameters should be and to try to do the design. And so it isn't quite clear how you should count that. But it is clear that people learn faster than these networks, and I believe it's because people make more assumptions about the domain. Now the second question had to do with, gee, in this case it looked like there was a sharing of features, and there was. It turns out that the reason that there was a sharing had to do with the fact that there was some analogy, actually, in this case in the color domain. There were some similarities in the colors that went across these birds and flowers and fish and trees just by happenstance. So it can share features when there are similarities that go across. Now in this case it didn't always do it. If I ran the experiment again, it might not have shared those features. It might have missed that particular possible generalization. However, the important point is that it uses the configuration of features to make its decisions about what to do. This didn't yield any mistakes, even though the analogy wasn't perfect. Because it can use combinations of features in making its decisions. And since the combination of plant plus animal is distinct, or plant plus, say, feature 4 being on, the first, say, feature 1 and feature 4 are different than feature 1 off and feature 4 on, because it can use the pairings and the combinations. So it causes it no difficulty. And sometimes it is worthwhile if there are these analogies that cut across these similarities that cut across categories. In those cases, you really want it to pick up on that. Yes?
Yeah, I have a comment and a few questions. As far as not having assumptions, it seems to me there is one sort of meta-assumption, which is that everything you show it is relevant. So that's sort of a major assumption. You have a lot of raw data. Somehow there's an assumption that everything is relevant, and so similarities happen not necessarily only between relevant people.
Yeah.
And that would be a drawback versus something that has more knowledge that points to what features in fact of the data would be relevant to the intended.
Well, of course, two comments about that. It has no trouble learning to ignore irrelevant things. If there is no predictive property of any particular part of the input, it simply ignores it. This is not a problem. Now, I don't want to say that it's a virtue that there are no assumptions here. It's in fact not a virtue overall, because it does mean that it takes more data to constrain it. And very often we work very hard to design the networks so that they do have assumptions built into them. If they're things we're certain of. If they're things we're not certain of, then we will not want to build these assumptions in. As just as a practical matter. If you want to build a system that will learn more quickly, you build in more assumptions. So I'm not opposed to building in assumptions. It's just a fact that on whole, there aren't very many assumptions in these examples, anyway, that were built in to the network. There were some. For example, that the spectrum was a good thing to look at in the sonar case. Obviously, that was a built-in part of the design. But if certain frequency domains of the spectrum turned out to be irrelevant to the decision, it would pay no attention to that.
That leads me to the question is there, say, networks that are built first by an expert or expertise of the way they're initialized, and so you're not starting with a tabula rasa representation? Are there applications?
There are methods. For example, suppose you have an expert system that's been say, hacked together that doesn't do a perfect job but captures a lot of what you want. You can actually use that as a trainer for a network. You simply use this, you simply use the expert system to train the network, and that will start the network out at a point in which it knows a fair amount of stuff. Now then, from then on in, the learning algorithm will modulate and modify and deal with exceptions and so on and so forth in order to train the network to do a better job. But you can begin, and this is not a bad strategy, to begin by...
Has that been done in the past?
Sure. No, we do that. You just build a little computer program to train the network to get it started. It's no problem if you want to do that.
We're out of time.
Okay? We're out of time.